Welcome back. I do have your tests. You can pick them up during the break. Today's going to be the last day I'm going to bring your tests to class. Henceforth, I mean, it's not relevant to you, but if you're listening to this on the recording, henceforth, you can come to my office after class to pick them up. Essays are being marked. They are currently being marked. I hope to get them back to you on Tuesday. They're looking pretty good so far. Looking pretty good. Mixed, of course. I mean, not every single one is a home run, but pretty good. Pretty decent. We got any course business? Anybody got questions about where we're going, what's going on, that kind of thing? No? Okay, so let's get into it. Please excuse my substantial sweatiness. And I can't tell, is this room currently a reasonable temperature? Okay, good, good. There has been some concern about that. I can't tell because I was almost late and had to hustle here, and therefore I'm overheated. I'm both hot and cold at the same time right now. Okay. So, where were we? So last time we finished off talking about the frame problem. This is this problem about how is it possible to intelligently ignore practically every bit of information that's available to you. And we had it, of course, in this adorable story about the robot trying to acquire a battery to keep itself going, but the battery's on the same wagon as a bomb. And we had it first just deduce that it was going to be able to get the battery, and then it blew up. And then we started deducing the side effects of its actions, and it stood there deducing irrelevant side effects until the end of time, or at least until the end of its time, because the bomb blew up. And then we had it, we finally installed this really almost quite improbable, I would say, quite improbable additional unit on this thing, which is able to tell what's relevant from what's irrelevant. So it's kind of a stretch of the imagination to suppose that you could give a good old-fashioned AI system a relevance detector, because that means you'd have to program an algorithm that can tell what's relevant. And it's really not obvious that that's possible. But even supposing that that was possible, the robot nonetheless died because it had to sit there going through the list of infinite list of possible things that it could deduce and either marking them as relevant or irrelevant. And so even with the relevance detector unit, the piece of its mind that could tell what's relevant and irrelevant, if you're doing a kind of good old-fashioned AI reasoning, well, it's really hard to say how it would, even with that improbable unit, do the kind of things that we do, which is, of course, to just ignore stuff that's irrelevant almost all the time. Like, it's not the case that you will always pick up on only the relevant information, but sometimes we can like most of the time, you don't pick up on most of the irrelevant information. So if I walk from one side of the room to the other, that changes my position with respect to Venus, and it really doesn't come up most of the time, right? So somehow we're doing this, and this is supposed to be something of an argument that it's, well, there's a few ways you can take this. One way is you're not going to be able to do this with good old-fashioned AI, because good old-fashioned AI is explicit logical deductions, logical operations on explicitly represented sentences, and usually, if it's a standard computer architecture, that's a serial process, right? It's one logical operation after another, and those lists get really long, really fast, and you'll basically hit combinatorial explosion. So that's where we ended up. Thoughts on this before? So I'd like to talk about a couple of potential strategies for dealing with this, but thoughts on this before we get into that? Yeah.
Ask a couple questions.
Yeah.
First is, as you're going through a problem, say it's polarizing a robot.
Yep.
There has to be kind of a point where, like, you progress through the current frame, and it'll look different than the original formalization. Like he talks about that a little bit about like having to give up, or you don't have to worry about the other stuff that you've already solved. What kind of parallels existed out in psychology of what we covered? Is that insight or intention? Because there's reframing, but there's also being somewhat through your current frame and then not having to worry about other stuff.
Yeah, so I would say the parallels, so what's the parallel in psychology? The parallel in psychology would be that stuff about problem formulations. So the question here is, how does the robot come up with the relevant problem formulation?
Does it update that? Like, it would seem
of course.
like it would have to update that as it's going through. Because, like,
Well, I mean, would it have to do that to be intelligent? That yes, absolutely it would. I mean, to be a properly intelligent agent, yeah, you have to. So you're either faced with a problem formulation that's so wide that you could never deal with it, or narrow enough that you can, but that means you have to update your problem formulation as your situation changes.
I was going to ask, regarding also to like formalization, formal system. If I wanted to formalize it, like I either have to go really big and like consider every possibility, or like with my formals, or would I have to have like a separate formalization of a half solved problem, a quarter solved problem, a 1/16 solved problem, whatever.
I don't know what the second option. I don't understand the second option. So
let's say instead of like coding for the entire scope of a game, you'd be coding for only the scope of half the game.
oh, I see. So probably it's the second thing. I mean, given how humans act, so we're the only model of genuine intelligence we have. We operate under heuristics, of course, which is a sort of like having a half-solved problem. That's like, a heuristic is like having a solution that works some of the time in some contexts. You haven't solved the problem, but you kind of got a way of surviving it for today. That's what a heuristic is. And we look very much like we're heuristic machines. So we operate under a whole bunch of we have problem-solving strategies. If you look at how people actually solve their problems, we have a whole bunch of strategies that look like heuristics. So that seems to be how we operate. And then the really hard question, the question that's sort of baffling from the good old-fashioned AI perspective is, how do you choose which heuristic? And that's in some sense shifting your problem formulation. So when you shift from one frame to another, you have somehow managed to say, that was the wrong heuristic and this might be a better one. Of course, we don't always do that perfectly, but we do that much better than sort of random chance would suggest. So yeah, so that's what we are, to summarize human life, we are stumbling around through half solutions to barely understood problems.
The other question I had was kind of related to the reading, as a previous reading of like good syntax takes care, the semantics take care of themselves if you have good syntax. Like
that's right.
Is that not also kind of falling into the danger of, I guess, emergent system? Because like if you set up a bunch of rules
Of what kind of systems?
of an emergent system, like if you set up a bunch of rules or a way of defining something, does then the reading kind of just spawn out of that?
Well, that's the hope. So you're quoting so Hausgelin says this, and he's speaking on behalf of the good old-fashioned AI people. He says, if you get the syntax well enough organized, the semantics takes care of itself. And is that a trap of the emergent system? I mean, I think.
Is that not just like an emergent system? It's a very
Well,
shallow
okay. So emergence is a funny word. Basically, it means something that is more than the sum of its parts. And maybe. So they're really not. They never figured out how to do this. So it was a task that good old-fashioned AI set itself that they utterly failed to achieve. So how that works is not clear because they never made it work. Yeah. Okay. So is the frame problem reasonably clear, like what the problem is here? In some sense, it's the problem of, so you can think of it in terms of problem formulation. You can also think of it in terms of belief updating. So this is one of the kind of classic ways of thinking about this. The world changes all the time, sometimes in small ways, sometimes in big ways. This robot is pulling a wagon. That's a change in its world. And the question is, what does it need to do to update its beliefs? And hopefully I gave you a strong enough argument in the psychology section that it can't be that it goes through every single belief it has and asks itself whether it needs to update them, right? That's too many beliefs. One by one, sequentially checking through every single belief that you could generate is way too many beliefs. So you need some constrained way of doing belief updating. And in some sense, what you need is some way of picking out which are the relevant beliefs to update. That's the problem. But of course, specifying an algorithm for relevance is super hard because relevance, like similarity, doesn't look like it's a thing in the world, right? You can't look at an object and say, this has 15 grams of relevance, right? Relevance is a relationship between typically some agent and some aspect of the world, and it's constantly shifting. The relevance of various aspects of the world is a constantly shifting kind of thing. So it's very, very hard to imagine how you're going to come up with a hard-coded set of rules for pre-specifying what's relevant. And in fact, what seems to make us intelligent is our ability to constantly update our rules about what's relevant. So you don't just come with some fixed notion of relevance. What you do is dynamically and in a context-sensitive way continually change what you think is relevant based on your circumstances. Doing that intelligently seems to be the core of human-level cognition. Okay, so this is one of the really profoundly deep questions in cognitive science. This is one of those questions that's so deep that even the people who defend the computational view of mind think that this is a deep, deep problem and maybe outstrips the capacity of the computational framework to solve. So Jerry Fodor, who I've mentioned a number of times so far, says this is one of those things that makes him think that computation can't be the whole story about cognition. Okay, so briefly, I'll just do a couple of strategies for maybe dealing with this. So here's one. It's called the sleeping dog strategy. This was the cutest picture of a sleeping dog I could find. You are welcome. So one way of dealing with this problem of belief updating is to do the following. You know the phrase, let sleeping dogs lie. So if there's not a good reason to update one of your beliefs, maybe don't update it. So assume everything stays the same until or unless you've got some good reason to think that it's going to change. Right? That's a strategy, a potential way of dealing with this question of how do I update my beliefs when things change in the world. So this is, I don't know, what do you think? Like, yeah.
Seems a lot like trial and error dressed up in a raincoat.
Yeah, maybe, yeah.
How do you determine what a good reason is?
Yeah.
It's just a mental fallacy.
Yeah. So good reason is just code for relevant thing. So that just lands us exactly back where we started in this question of what to, and I mean, you'll end up with all kinds of false beliefs in this too as well, right? So like, just because it's not relevant that when the wheels turn, the day of the week doesn't change, when the wheels turn, its position with respect to Venus changes, just because those are irrelevant doesn't mean that they are not true, right? Those are true facts about the world. It's just that they're not super important. So if you're just ignoring anything that's not immediately important to you, you're going to slowly accumulate false facts. Let me do a quick, this, yeah?
I was going to ask, like, kind of like fix this or improve this, like getting back to kind of problem solving formulation, people were given cues of like how to solve the problem better.
Yep.
Would you like, you still require some kind of cue here to change your strategy, like what relevance is?
Yeah, so, sorry.
So when we were doing problem solving in psychology, people were given cues of like how to solve a problem.
Some cues facilitated and some didn't, yeah.
You still need like a key here, don't you? Like, just even before you determine relevancy, it's like, okay, what I'm doing right now is not working out. We need to know that it's not working out, like, unless you know.
Right, exactly. This is very much what Lexi was saying, that it's what we've encoded here is the belief that you can tell what's a good reason and what's not to. So what's a good reason to update your belief? Well, that's just to say, which of my beliefs are the relevant ones to be changing? And that was the question in the first place.
So,
Yeah.
like, what belief then do you pick?
Yeah, that's exactly it. Yeah, that's exactly the question. Jerry Fodor's got a weirder kind of metaphysical problem with this one that I'd like to briefly go through. So this is from Modules, Frames, Phrygian, Sleeping Dogs, and the Music of the Spheres. Nobody writes like Jerry Fodor anymore. You can't get away with writing like this. You have to be super famous before you can write a title like that. Okay, so his argument is something like this. He says, Sleeping Dogs assumes that most of the facts stay the same most of the time. That is, that the world is basically constant most of the time, and that change is the exception rather than the rule. But what are the facts? What are facts? When I say a fact, what am I asserting? I'm saying that an object has a property, right? That's a proposition. A proposition asserts a fact. When I say something is a fact, I'm saying this object or set of objects has this property or set of properties. But properties are cheap and easy. You can make up properties as left and right, right? So here's a property that Jerry Fodor thinks that we should consider, a Phrygian. A Phrygian is a fundamental particle while Jerry Fodor's fridge is on. Okay? So anything that is a fundamental particle at the same time as Jerry Fodor's fridge is on is considered a Phrygian. Okay, so when he unplugs his fridge, the whole universe goes from being full of Phrygians to absent Phrygians. So a property that applies to every fundamental particle in the universe blinks out of existence, and then he plugs it back in, and it comes back. The universe is full of Phrygians again. Now, you, of course, if you're a sensible person, you're sitting there thinking, that's a dumb property. Don't make up properties like that. That's silly, right? That's what you should be thinking. That's not a helpful property. You didn't get through your day by thinking about Phrygians, of course. But what is another way of saying that is to say that that is an irrelevant property. That's a property that doesn't matter, that's not important or salient or something like that. So what you've done is made a judgment about which are the interesting or important facts. Hopefully none of you deny that that's a sense of, like, that's a coherent property in the sense that, yeah, you could say that if you really wanted to, right? You could say that. It's not like I just said nonsense, gibberish. Like you could parse it, right? You could evaluate the truth or falsity of the sentence, that particle is a Phrygian. Yeah? It's just that that's an irrelevant, unimportant, uninteresting, kind of weird property. And what that tells us is that your ontology, that's just the philosopher's word for your list of things that happen to exist in the universe. So your ontology is just your picture of what there is. Your ontology encodes beliefs about what's interesting or important. So you shouldn't put Phrygians into your ontology, probably. You shouldn't say, here we're going to make a list of the most important fundamental things that exist in the universe. Phrygians are not on the list. But that's just to say your ontology encodes judgments of relevance, which is again to say, which is sort of gets us back into this problem. So the sleeping dog strategy assumes an ontology of what are the facts in the world, right? And you assume that they stay still because you've got an ontology that lets you do that, which is just to say the belief that things mostly stay the same most of the time is a way of saying that you've got a reasonable way of parsing relevance in the world. Yeah.
Does that not lead though to kind of like the risk of just, okay, we're not going to consider anything imagined or made up or any kind of critical thinking, like, will the machine just then kind of expect, well, these are the facts, they're not changing, I'm not going to consider anything new, I just only what's in.
No. So he's not, the argument is not supposed to be don't generate new properties. That's not the point. The point is not that we shouldn't be allowed to generate new properties. The point is that your image of what the world contains, what the facts are, is relative to an ontology, and your ontology encodes your judgments of relevance. So you already need to be able to judge what's relevant to say whether things mostly stay the same or mostly change. That's the point. So there's judgments of relevance buried in your ontology, and your ontology is what makes the strategy work. So we haven't gotten out of the need to make judgments about relevance by adopting the sleeping dog strategy. I mean, you could say something like, were we all here last week? No. We were thousands of kilometers from here because the Earth has been spinning through the void and the sun has been going around the galaxy. Everything about our location, I have never been in the same place twice ever. But that's not relevant, is it? We make our judgments about location relative to our human scale lives, what's important and interesting to us. So, hey, did my position change? Not from my perspective. Not from my way of parsing what is in the world, what the facts are. From some broader perspective, yeah, I've never been in the same place twice. I recently got an old friend got in touch after I hadn't seen this guy in 20 years. Literally every molecule in my body will have cycled through in those 20 years. So I have no common molecules with the last time I saw him. but I'm still me, right? So that kind of, there's some persistence across change because of the way I parse the world. Right? So what stays the same and what changes is relative to what you think is important, because that's what sets up what the facts are. Okay, this is a philosopher's criticism, really. Like, this is not the kind of thing that a computer scientist would worry about. But I do think that it pulls out some interesting questions about, like, some interesting facts about how deep judgments of relevance are in our worldview. Right? Your very picture of what exists and what persists encodes your judgments about what's important. So you can't rely on those things in a sort of, I mean, the temptation is to say, look, let's just deal with physics. Let's just pay attention to what science tells us is objectively there in the world. And that's what will generate our judgments of relevance. But what I'm trying to show you is that that's not going to work, because we constantly flexibly navigate those myriad possible properties you could pick out as the ones that you're going to identify as the real properties, and fixate on the important ones, the interesting ones, the ones that keep you alive and whole and healthy, as you should. That's an intelligent thing to do. We don't just say, well, position is just whatever physics says, so I've never been in the same place twice. No, you say, come back to this classroom on Thursday, right? Yeah.
Does this not matter, like, we're supposing, like, across a range of contexts, which somebody will find themselves in, or a machine will find themselves in, there has to be some kind of similarity across all of these. Like, is that really what it's getting at? Because that seems like a very interesting comparatively to, like, how we do categorization, or
Right.
what we find relevant in a situation. So,
Right. Yeah.
does that not fail here miserably?
What?
Like,
Sorry.
that commonality, like,
Well,
is there really a commonality between contexts like this in this survey?
oh, contexts are very similar. The different contexts of your life are very similar. But remember what similarity is. It's a judgment that these are relevantly similar. Remember back in categorization, we said two things are not just similar, they're similar under some point of view. We might say under some framework, some frame on which you put on the world. So yeah, the contexts across your life do have really important similarities, but don't treat similarity as like it's a feature of the world. It's a relationship that involves how these things matter to us. Okay, let's do one more strategy and then we'll leave this. So, maybe the problem here is this serial processing stuff, one thing after another. That seems like a clunky way of dealing with the world. Furthermore, you're probably aware that the brain has got a bunch of stuff going on all at the same time. There doesn't appear to be any central processing unit in the brain as far as we can tell. It's not like every neuron is wired through one central locus, right? It's all kind of parallel. So maybe that helps. Actually, I think it does help. I think this is part of the answer. So maybe instead of just one serial processor, the strategy is, let's have a bunch of parallel processors. So I think there's actually something to this, but it gets us into some really interesting questions that we will come back to when we talk about consciousness. So here's the wedge question. Here's the question that kind of pries this strategy apart. Do those parallel processors talk to each other, or don't they? And to what degree? So there's a view in evolutionary psychology mostly that the brain is made up of what are called modules. So a module is a little specialist processor unit that takes in only a very few inputs. So the evolutionary psychology people say stuff like you've got a face detecting module. It's just one part of your brain. Its only job is detecting faces, right? So that's a specialist system. And you can imagine how you could get currently we've got AI that does facial recognition. So this isn't like, oh no, there's no way to possibly mechanize the process of recognizing faces. No, we've done that. We know that that's a specialist subsystem that you could isolate. You could just say, I'm just going to feed it the things that I think are maybe faces, and you're just going to tell me what face you think that is, right? So a very limited number of inputs, very limited number of outputs, and a kind of specialist processor that does the processing to turn the inputs into outputs. So that's what a module is. And there's pretty good evidence that our brain has got a bunch of this sort of stuff going on in it, right? There's lots of specialist systems, and you can tell that by the fact that, sadly, unfortunately, lots of people have undergone traumatic brain injury or stroke or something else that knocks out one of these specialist systems. And you can get very specific losses, right? So you can very specific deficits, which tells you that there was something very specific doing that job. So here's a picture. Maybe those maybe we're what they call massively modular. Maybe we're just a whole bunch of specialist subsystems all working away kind of independently of each other. So what makes something a module is that it doesn't know its context. It doesn't know the global picture. It is what they call informationally encapsulated. All it knows is like a couple of little inputs. And that's how it's able to be a specialist subsystem. That's how it's able to not have to deal with the global situation where it would face combinatorial explosion. So there's a picture. Maybe we're just a bunch of, this is not from evolutionary, I think it's from phrenology or something. I don't know what this picture's from. Anyway, so that's a picture. Maybe we're made up of just a whole bunch of specialist subsystems all working away independently in parallel. Yeah. So this is Steven Pinker wrote a book called How the Mind Works, where he basically argues that this is how the mind works. What you've got is a whole bunch of independent subsystems all working on their independent problems, and that's it. So when you have the frame problem, really what you're worrying about is the global connections between things, right? The long distance connections, and maybe we're just not built that way. So that certainly gives us a picture of how the brain could break down into little algorithmic processes, but it doesn't seem to be, let me just poke a hole in this right away. I don't think that can be the whole story, because one of the things that we can do is make long distance connections between ideas. So I put the model of the Bohr model of the atom up there. Is that Bohr or Rutherford? I think it's Bohr, who came up with the analogy between the atom and the solar system. So they were trying to figure out what the structure of the atom is. They knew what the structure of the solar system is. They had a few different ideas. One that it's like a beanbag, right? It's just a bunch of, or like a cookie model, like the electrons are baked into this cookie of the nucleus. And on the analogy to the solar system, we get this quite, and it's not the correct picture, but it was a big advance over the models of the atom that came before it. And that's a kind of long distance connection. Hey, maybe this microscopic thing is like the solar system that we're embedded in. And you don't usually find that. You don't like, maybe this protein is the same as Europe, right? That's not an expected connection. It's not a connection that would come from just working in your little local subsystem, right? So, I mean, this is just an example. Analogies, metaphors, surprising connections that can be made between things. The whole discipline of cognitive science is based on the idea that we can do this in a productive way, right? So the human capacity to make long distance connections. Recall also the stuff when we talked about insight problem solving. We talked about trying to find solutions to a problem in little memory compartments. And the fact is that lots of the most creative solutions to problems, the ones that involve the most insight, often involve stuff from different compartments. Right? You're putting things together that you wouldn't have expected go together, and that's what an insight is. So the human capacity for insight seems to be impossible to imagine if all you've got is a bunch of independent subsystems not really talking to each other. Yeah? What you need is some global system, right? So to be clear, I'm not saying that we don't have a whole bunch of independent specialist subsystems. I think that's actually probably true of a great deal of the mind. A great deal of the human mind is probably a bunch of independent, parallel operating subsystems that have specialized jobs. But it's got to be the case that somewhere in there, there's a global and unencapsulated part of the mind. This is the conclusion that, for example, Fodor comes to, that you just cannot have an exclusively modular mind because we're able to do things like insight, analogy. We're able to do things like decide which heuristic to use. So imagine that these little subunits are different heuristics. Now, which heuristic do you employ to deal with the situation that you're in? How do you decide what kind of problem you're facing? Those seem to be the kind of problems that you actually need to know not just some small collection of details, but the global situation that you're in, right? The capacity to be sensitive to context, all of this stuff requires openness in the information processing that information encapsulation denies. So we got two options. You can either have a completely informationally encapsulated, what they call massively modular mind, that's just a bunch of isolated subprocessors, which is hard to imagine how we could be humans if that's how we are. Or you can have at least some of them be informationally open. And then it becomes utterly mysterious how you do that, how you deal with things like combinatorial explosion, how you deal with things like assessing relevance, context sensitivity. And it's especially mysterious how we do that using the good old-fashioned AI model. So Shanahan, 1997, asks, how is it possible for holistic, open-ended, context-sensitive relevance to be captured by a set of propositional, language-like representations of the sort used in classical AI? I don't think that I've given you an argument that that is utterly impossible, but the evidence, so we've got a few converging lines of evidence. One, there's these deep theoretical problems like the frame problem. So the frame problem is a problem that emerged from trying to build minds in computers using the good old-fashioned AI structure. So it didn't occur to anybody that this was a problem until we actually tried to build minds. And things like combinatorial, as we saw back in the problem-solving stuff, things like combinatorial explosion just didn't occur to us until we tried to actually build one. And then there's a sort of theoretical problem. And then there's the practical history of this stuff. So in the process of actually trying to build these things, we not only a bunch of like deep theoretical questions came up, but we just failed. It just didn't pan out as a practical research program. So it's not the case that there's no good old-fashioned AI around. There's good old-fashioned AI kicking around here and there. Anytime that you can take a problem and boil it down to something that you don't have to be contextually sensitive for. Anytime you can boil a problem down to something where there are clear rules that never have to change, you can find good old-fashioned AI. It's very efficient. You can make really small little nice programs that do the thing, right? So if you can boil it down to a rule, good old-fashioned AI will do it. But for things that you can't boil down to just simple rules, it is radically unclear. Again, we've got these theoretical problems, and we've just got a long history, decades and decades, of practical failure of being unable to deal with these problems in an engineering sense. So those are two prongs of the argument for why good old-fashioned AI just wasn't up to the task, at least in terms of doing a kind of like strong AI cognitive science research program about how our own minds work. So, what's next? Neural networks and connections. So, the idea here is that they've got an alternative to AI, or good old-fashioned AI. The hope was that this would be an alternate research program that we could sort of like get out from under some of the basic questions of no problem. Yeah. We're not getting visited as much as we were during graduation, at least. That's nice. Okay. So this is pitched. The way that this was pitched to the world was as a deep alternative, a radically different proposal for how to organize artificial intelligence and therefore how to model the human mind. And one of the deep differences is supposed to be that these things are not, connectionist networks are not computational in a certain sense. So it really depends what you mean by computational, what is a computer. That's partly why we went through in such possibly excruciating detail Hausland's definition of what a computer is, because they had the good old-fashioned AI people had a very specific idea about what computation is. It's formal symbol manipulation on sentence-like structures using logical rules, right? That's what they thought it was. You could define computation more broadly in terms of just any kind of information processing. So if you're willing to accept any kind of information processing as computation, then these things are also computational. But that kind of trivializes the word computation, because information is one of those words that, I don't know, information is one of those words that escaped from the zoo. I don't know if you've been following this. Like, it's everywhere now. So physicists talk about information being in the world. So like literally every physical process in some sense is information processing. Information has gone wild and it's just everywhere now. So if you're willing to say anything that is information, dealing with information is computation, then biology is full of information, physics and chemistry are full of information. Information is everywhere. So what they're denying is that this is computation in the classical GoFi sense. They're denying and also that thinking propositionally is the basic operation of your mind. So that's basically what they're denying. And your reaction to that probably has a lot to do with what kind of maybe personality you have, what kind of life you're living. Some people are profoundly identified with the internal monologue that goes on in their heads, right? Such that they can hardly imagine any kind of mental life without that thing. Like that internal monologue is their access to their own mental life. But I bet that you mostly don't need that to get by in the world. So like when you walked in this room today, you didn't say, there's a wall, the floor is solid. I see a chair there, I think I will go sit in it. I believe that's the chair that I sat in last time. I will pull the chair out and then sit on it by bending my knees. Was that a little bit? Yeah, a little bit, okay. I mean, some of that, there's gonna be some of that. But you could have done it without that. You could have had going through your internal monologue, you could have been like, oh man, I shouldn't have said that to her. Boy, I really embarrassed myself last night. I gotta lay off the caffeine, Like that could have been your internal monologue as you're going to get down, sit in your chair. You would have sat in your chair just the same, right? So the GoFi view was that your mind is basically made of language. The basic stuff that it's composed of is language and the manipulations on language. Whereas the connectionists suggest that no, that's not what your mind is fundamentally made of. Of course, if this is going to be a theory of mind, they have to at some point tell us how we do use language, because we all use, I marked your tests, I know you can all use language. So somehow we do get language out of the mind, but that's not necessarily to say that the mind is made of language, right? Or that its basic operations consist of language-like manipulations. So that's a kind of deep difference between what they think the mind is composed of. It's a fairly radical, and there are lots of people in the school with different degrees of radicalness. So some of them talk about like a mind without representations. Right? So it's not a representational architecture. Some people are willing to say, no, there are representations, they're just a different type, they're not language-like. So there's a debate about that, but this is the basic idea. Another kind of deep difference between the good old-fashioned view and I'll just say GoFi, the GoFi people and the connectionists was that the GoFi people didn't care too much about brains, did they? Wasn't a lot of talk about brains the last couple of weeks. Whereas the connectionists explicitly sell their product as being a kind of brain-like architecture. So build something that looks more like the brain. That's not to say that they lose multiple realizability necessarily. right? So you can build a connectionist network in hardware, in software. It's multiply realizable, but it's more brain-like. It's kind of an artificial brain built up out of artificial neurons or something like that. So these things are called neural networks, and the idea that they provide a good model of cognition is called connectionism, also called parallel distributed processing, something like that. It's had a bunch of different names over the years. So this view, I'll just show you a Google Ngram. So do you all know Google Ngrams? These are magical things. I love these things. So if you want to know how an idea moved in and out of the world of books, Google Ngrams are the best tool. It's free. You just type in any term, and this what gives you a graph of, you can't really, I'm sorry, you can't see very well, but this is 2005, 2000, 85, 80, 65, 1950. And so this is a timeline, and this is just how often that word appears in books. So you can see a kind of timeline of an idea entering, not the culture as a whole, but literary culture, the world of books, and as it moves in and moves out. Unfortunately, it ends at 2008. I can't wait for it to move forward in time. Surely it'll do that. You can look at Google, for 2008 and on, you can look at Google Trends, which tells you how often something is searched for on Google. So if you want to stitch together a picture of something going in and out of the culture, and here is neural network. And you can see up till 1985, it's not zero, but there's not a lot going on. So mid-80s, and it starts to explode mid-80s through 95, and then the 2000s, it starts to waver a little, and then by 2005, it's kind of tanking. It's kind of tanking. So this is more or less, I would say, an accurate representation of when this stuff kind of got hot and as it trailed off. If you look at the Google Trends line from 2004, it just kind of goes down from there. Which is not to say that neural networks have stopped existing. It's not to say that they've stopped being important parts of computer hardware, or sorry, computer software. They're still like useful tools, but they haven't got the kind of cultural zeitgeistiness that they used to. Some more advanced versions of what we're going to talk about today go under the name of deep learning, and we'll talk about what that means. So today we're going to talk about the history of this stuff, kind of where it came from, its development up until, yeah, probably like 95, 2000, somewhere in there. And later we'll talk about where it goes from there. So deep learning is a kind of very specific type of these things that went beyond what the ordinary connectionist nets were capable of. So that's the kind of arc of history of this stuff that we're going to talk about. Right. I was informed during the break that the Google trend for neural net is back up. It's heading back up again. So we're currently undergoing, in the last few years, a resurgence of this. So it was a dip from like 2004 until what, like 2011, 2012, something like that. So there was a pause, and then we developed some nicer, better algorithms that did a bunch more stuff. So we're coming back. All right, so these things are supposed to be neural networks. They're supposed to be, let's get into the nuts and bolts of how these things work. We're really just going to do the basics, like really just the basics. I am not qualified to teach you how to actually build one of these things. So don't worry, do not succumb to math panic, because there's not going to be any. But they're supposed to be modeled after brains, right? So let's think a little bit about how neurons work and we're just going to pick out like a very limited set of the things that neurons do. So this is a pretty simplified model of a neuron that we're just going to think about three features. So it fires, of course. Neurons firing is, of course, sending an electrical signal down the axon. Is that right? Dendrites are where it gets its signals. Axons are where it sends out its signals. That's right. So these are the dendrites on the left. The firing rate is how often it sends an electrical signal kind of down its arms, right, to stimulate other neurons, basically what they do. Those firing rates affect other neurons in one of two ways. They can either be inhibiting their firing rate or exciting it. So you can either be saying quiet down or speak up, right? Those those are the two things that these neurons can do to other neurons. And then there's the weight of the connection. So just because it's at a certain firing rate doesn't mean that it's necessarily inhibiting or stimulating the other neuron the same amount. You can have a weighted connection so that some neurons speak more loudly to each other than others. So let's just leave it at that. Those three features those are real features of real neurons. There's a bunch of other things that neurons do, lots of other properties that they have, but we're going to ignore them all because none of them turn up in connectionist networks. Like, notice that there's no neurotransmitters here, right? Neurotransmitters diffuse. They don't go down the axon. They just sort of diffuse into the general area. And as we know, you need your neurotransmitters. They are essential. If your neurotransmitters aren't working, you're having a really bad time. Let's pretend those don't exist. Okay. So so the firing rate is just the speed at which it's going. That's fairly straightforward, right? So faster is more excited. Inhibition or excitation is just whether some part of your brain is on or off, whether it's doing a lot or not doing that much. Let's talk a little bit about weight of connection, because this one we actually have you have some phenomenological access to. You have some first-person access to this feature. So different parts of your brain, generally speaking, all of the parts of your brain have reciprocal connections. So if there's a connection between part A and part B, there'll also be a connection between part B and part A. So they're all mutually wired together, but those mutual wirings are not all of the same strength. And this is a good way to organize the brain, actually. So here's your amygdala. This cute little guy right there. It's adorable, right? Okay, so your amygdala, amongst other things, is the part of your brain that gets really excited when you think you see, for example, a snake. So your startle response, you go, "Dah!" Right? That's your amygdala going, "Dah!" It's a very old part of your brain. It does things like the startle response. If you go into a shed at night and you think you see a person there, you're like, "Dah!" That's the amygdala. It goes very fast. It's very vivid, right? It has very strong forward connections, right? So it's deep in your brain, very strong forward connections. It also is the part of your brain that does things like, I don't know if this ever happened to you. My most vivid memory of being a kid at the mall was when you lose track of your parents and you're like, "Oh my God, where are they?" Right? So that feeling of, "Oh my God, where are they?" is your amygdala going off. So these are all like, I mean, if you get lost at the mall, you're gonna get found eventually, right? But in our evolutionary context, getting lost on the African savanna was a genuinely dangerous situation to be in. Spiders and snakes were genuinely dangerous features of your environment, so you want to be really attuned to these things, right? And you don't want for the front part of your brain, your neocortex, the thinky bits, you might say, you don't want for the thinky bits to be able to override that. So like, you don't want to be able to just say to yourself, "Wonder what it would be like if I wasn't afraid of heights." And then you weren't afraid of heights, and then you fall off a cliff, right? You don't want to be able to override those really built-in, deep, dark, old parts of your brain. You want those to have very strong access to your neocortex. It has substantial downsides, though. So, for example, if you've ever experienced losing somebody who's very close to you, right? Your amygdala goes off and says, "Go find them, go find them." And your front brain says, "They're gone." Right? The amygdala speaks very loudly to the front brain, and the front brain says, "They're gone." The amygdala says, "Go find them, go find them." You say, "They're gone." And it takes years for the front brain to convince the amygdala. Sometimes a year, 2 years, 3 years, longer. And like, that's grief. That's the feeling of grief. When different parts of one part of your brain is sending a very powerful forward signal to the rest of your brain. to the neocortex, and the neocortex is perfectly aware of the situation. Like the neocortex is like, I broke up with her. You know, like we left on purpose, amygdala. We didn't like it there anymore. But the amygdala's got the neocortex has relatively weak speaking back to the old parts of the brain. Okay. Sorry, it's a grim sort of story, and I don't have a story about the other two, but I found that this was part of the original cognitive science course that I took back in 2001. It's one of the bits that stuck with me the most, so I thought I'd share it with you all. Okay. So enough of real brains. Let's talk about fake brains. So basically a neural network, in the sense of connectionist neural networks, you can characterize them by essentially the following three properties plus a learning algorithm. So there's these three things plus something to change these things. The firing rate, so these circles here are, we're going to call them neurons. You might call them nodes, right? They're just essentially just a little function that takes in a number and spits out a number. That number we'll call the firing rate, something like that. And then you've got whether it's a plus or a minus, whether it's inhibitory or excitatory, and you've got the weight of the connection. So suppose we've got inputs feeding into these nodes. The top one there is excitatory, it's a plus, and it's got a firing rate of 5. That means, and the weight is times 3. So that means it's got a 15, it's exciting this thing by 15. This one's got a plus 10 times 1. It's exciting this thing by 10. This thing is got an inhibitory firing rate of 6, weight connection 2, so it's down by 12. So this is reducing this number by 12. And I checked this on a calculator before I came here today, and it adds up to 13. So that's how you get the total activation of this is a function of the firing rate, whether it's inhibitory or excitatory, and the weight of the connection. This is the kind of really simple version of this. The actual functions can be substantially more complex, but that's the basic idea. And that's really all a neural network is, those three things. And notice that none of those are symbolically structured linguistic representations. Right? None of the internal activity of this thing is saying anything propositional. Okay, so with that in mind, let's go through a little bit of the history of these things. So the very first one, built in the 50s. We barely had computers in the 50s. Just barely inventing these things. And the first, they called it, boy, they could name stuff back then, the Mark I Perceptron. That's what this was called. Built for the Navy, and its job was to categorize things. So this thing had about 400 input nodes. Those input nodes were like photovoltaic cells, so they're basically just like 20 by 20 image recognition software. Not even software. This thing was hardware. So they built one in software originally, but the Perceptron Mark I was a purpose-built, hardwired neural network. And it took in, as I said, a 20 by 20 matrix of inputs, and its job was to classify things. Its job was to look at a picture and classify it into one or the other of two things. For example, you're the Navy, so one of the things you care about is rocks versus mines, right? The underwater mines that like blow up your ship. So your job, Perceptron, was to say, look at a picture and tell me, is that a rock or is that a mine? And it would output kind of one or the other. And its structure was very simple. Like it's just one layer. So over here we've got x1, x2, x3 to xn. In the Perceptron, that would have been x400 because there's about 400 inputs. So these are the inputs of like do you see color here or not? I think it was probably black and white. Do you see, how bright is the pixel that you're looking at, basically? And then we've got just as we said before, we've got connection weights on those things. So you got an activation rate, whether it's inhibitory or excitatory. You've got a connection weight, and then it's literally just a linear sum. You just add up the values from the nodes, from the input nodes, and if that sum goes above a certain threshold, you output a 1, and if it's below that threshold, you output a 0. That's it. So take in a bunch of inputs that are either that are weighted in various ways in either inhibitory or excitatory, add them up, literally just add them up, and then if they pass the threshold, output 1. If they don't pass the threshold, output 0. And like astonishingly, this thing can provably categorize things pretty reliably. So it could tell the difference between things in a fairly reliable way, assuming that the things met certain criteria. So it's a linear classifier. Linear classifier, that is to say, so this job over here, it could do very well. So the stuff on the left, we're going to tell cats from dogs. So if you can draw a line, literally it's a linear line, you can draw a line between the two different things, then the perceptron is able to do the classification job. And you can prove that it will eventually, given the right learning algorithm and enough trials, it will converge on successfully distinguishing the two types of things, assuming you can draw a line through them. The problem happens when it's something like the thing on the right here, where there's no line that you can draw between those two, between the blue things and the green things, right? So I'm sorry if anybody here is blue-green colorblind. There's some blue things and some green things. So there's no straight line that you could draw between those two, right? You could draw a curvy line, but Perceptron can't handle that. Perceptron can only deal with straight lines. It has to be linearly separable. Remember that from prototype theory? So prototype theory also required that things be linearly separable. I promised we'd come back to it. We came back to it. And now with a much better diagram, not just my weird oranges and fruits and stuff. This is a much better diagram of something that's not linearly separable. So for much the same reasons, actually. So prototype theory, if you recall, just a prototype is just a list of features weighted by their salience. You either have the feature or you don't have the feature. Perceptron is a collection of inputs weighted by the connection weight, and you either have the input or you don't have the input. You're either inhibitory or excitatory, and you just add it all up. You just linearly sum up the values of the inputs, which means that it's perfectly able to do linear separable categorization tasks, cannot handle this. The good old-fashioned perceptron. So that's one kind of deep limitation of the earliest versions of neural networks. It's certainly not current neural networks can handle this fine. Neural networks today can deal with this no sweat. But the earliest version of it, the perceptron, could not handle this. So that's one limitation. Another one that they kind of stumbled on and started learning about how you needed to treat a neural network happened with, they were trying to teach one of these things to distinguish trucks from tanks. And so what they do is they give it a bunch of pictures of trucks and give it a bunch of pictures of tanks. And when it gets it right, they say, good perceptron, have a cookie or whatever. You know, like we'll talk about learning algorithms in a little bit. But so you have to give them a bunch of data and tell it how well it did on classifying the data. And so they give it a bunch of pictures of trucks and a bunch of pictures of tanks. And it got pretty good. It could reliably distinguish the trucks from the tanks in the data set, in the original training set. And then they would give it some new pictures, and it could also distinguish trucks and tanks. It's the kind of thing the Army really likes, right? You would love to know whether the thing is a truck or a tank. The problem was somebody had gone out. They probably did it in a day. I don't know the details of the story. In the morning, they took a bunch of pictures of tanks, and in the late afternoon, they took a bunch of pictures of trucks. So what Perceptron was distinguishing was high luminosity, bright pictures from dark pictures. So if you gave it a picture of a tank in the late afternoon, it would be like, aha, that's a truck. So it was reliably classifying a major difference between the two categories it was trying to distinguish. It just wasn't the one that you thought it was, or that the military hoped it would do. So this is the problem of having the right kind of data to train it on. And this remains an issue. So the linear classification thing, we got that solved. You still have to kind of curate the data that you're giving to a neural network to get it trained up properly. You have to carefully spoon feed it. Yeah.
Isn't this an issue with people too? Like,
Yes.
you have too many words, say, okay, these are X's, these are Y's,
Yep.
and give them two sets of pictures, people could just easily grab onto the wrong distinguishing feature. Like,
Yep.
you could be bad at pattern matching.
Absolutely, absolutely. And you do have to carefully curate the data that you give to people. That's absolutely true. We are reasonably robust at doing this, though. So you can do things like tell people, no, the tanks are the ones with the pointy bits on the front. And they add that under their classification scheme and radically alter their classification scheme. Even if it's, look, this picture's much brighter, that must be a truck. No, that's the pointy bit at the end, shoots death. That's a tank. So we can leverage a bunch of stuff that looks a lot like good old-fashioned AI, actually, we can leverage. We can leverage reason. We can leverage definitions. We can bring in a bunch of, causal reasoning or classificatory, propositions that alter the way that we think about things. You do have to curate data for people. You can't just give them a bunch of random data. I'm invested in thinking this because I'm employed as a teacher right now. So I have to assume that I can't just throw a bunch of information at you and let you just sort it out for yourself. I am really trying hard to curate the data that I'm feeding you. But what we learned was that you have to, at least for the perceptron, you have to really know the categories well and then feed it the data that would accurately represent the categories pretty carefully, or else it will make these kinds of errors. I take it this is a general problem that there is lots of good methods for dealing with in statistics. The overfitting problem, yeah? So this is a thing that statisticians have been long been dealing with. We just rediscovered it in the context of perceptrons. Okay, so the perceptron. It looked like it was going pretty well for a while. It's got some limits. It's got some fairly serious limits. And then this thing happened. So here's an odd little incident in the history of science. This happens sometimes where our research program gets derailed for maybe unfair reasons. And there's some debate about exactly how this went. But so Marvin Minsky and Seymour Papert wrote this book, Perceptrons: An Introduction to Computational Geometry, where they proved mathematically that the perceptron couldn't handle the following fairly straightforward logical operation, which is exclusive OR. So exclusive OR is, if I say you can have fries or salad, and you say I'd like both please, I say no, fries or salad. That's exclusive OR. You pick one or the other, right? Anybody have trouble with that as a concept? Fries or salad? You have to pick one? No? We all got that, right? Exclusive OR. Seems like it's the sort of thing you should be able to handle. Sadly, Perceptron cannot handle it. And they proved mathematically that there's nothing you can do with or for the Perceptron in order to make it able to handle this fairly straightforward logical operation. This is probably radically oversimplifying it, but I think I can show you how. I think I can show you why this is the case. So this is a much nicer graph. So A and B are the inputs. 0 is false and 1 is true. So for it to be true, for the output O to be true, it's got to be 0, 1 or 1, 0. Yeah? If we graph it this way, A, the input's 1 or 0, B, the input's 1 or 0, and these are the outputs, you can see that there's no way to draw a line such that you get all the zeros on one side and all the ones on the other. There's no way to linearly classify this function into ones and zeros. So therefore, Perceptron cannot handle it. I think their proof was a lot more rigorous than that. So I'm thinking to myself, yeah, but maybe you could rearrange the graph somehow. They actually provide a mathematical proof that Perceptron can't handle this. And so here's where the sort of history, sociology of science gets a little bit unclear. One way this story is told is that Minsky and Papert argue that not only can Perceptron not handle this, but fancier neural networks would also fail. That it doesn't really help that much to make the neural network fancier. And so that's one way the story is told. Another way the story is told is that Minsky and Papert were much more careful than that. They say, look, this is just a perceptron problem. We are not making any claims about the fancier neural networks. But then the good old-fashioned AI people kind of seized on this argument to say, aha, your research program is garbage. Give us the grant money. And so Minsky and Papert weren't actually saying that don't do this neural network stuff. You know, maybe fancier versions would do something. We're not saying anything about that. But the story the way the story gets told is they proved that this neural network stuff is hogwash, and then it literally goes into the basements for like 20 years. Like, people stop spending research money on this. They start dumping research money into good old-fashioned AI. So from the 70s to like 1985, so 15 years or so of almost total obscurity for this as a research project. And it may have been sort of their fault. There's a debate about whose fault it was that this thing got kiboshed, but what we know now in retrospect, so enough history of science, what we know now in retrospect is that adding layers does a whole lot. So recall, Perceptron was just like one of these input layers and then a summation unit and then output. That was it. That's all Perceptron was. These things in the middle, called hidden layers, make it capable of doing things like exclusive OR, nonlinear classification. So this is the kind of basic structure of a normal, like vanilla neural network. This is the kind of stuff you would have seen in the 80s, where there are input nodes. So there's an input layer where they take in some information from something. And then there's a couple layers between the input layer and the output layers that do, like, they're hidden layers. They don't output anything except to the deeper layers. And you can put as many of these layers as you want. You can give them as many nodes as you want. And this makes these things much, much more capable, much, much more robust. They could do a much wider range of stuff. Yeah?
How do you determine the properties of the hidden layers? Like, you just do more types of processing on the data?
So the properties of the hidden layers are just exactly the same as I described. It's just the same three properties as what I described for these. So they're connection weights. So these are weighted connections. These are also weighted connections.
How do you determine like the weights and stuff for that?
Right. So to determine those, you need at first, usually you just set it to random, and then you apply a learning algorithm.
Okay.
So the learning algorithm we'll have to talk about in just a little bit. So, yeah. So yeah, that's the bit we haven't talked about yet is how do you figure out what the weights should be? How do you tune this thing up? That was in Perceptron. In Perceptron Mark 1, by the way, that was literally electric motors that would change the weights of these things. Okay, so this is like just to bring this back to the difference between this and the GoFi picture, in some important way, the input layer represents things. It's like if you're doing image recognition, each one of these is a pixel, right? So you can say, what's this thing? Well, it's a pixel. And if you're doing so image recognition for like recognizing handwriting, then each one of these represents something too. It's like this one is A, that one's B, that one's C, and so on. But the hidden layers don't really represent anything as such, not necessarily. Maybe you can glean some kind of rough idea of what's going on there, but there's no guarantees that that's going to be the case. It's just a kind of it doesn't contain a symbolic representation the way that you could read off of it in the way that a good old-fashioned AI program did. I think there's some kind of existential lesson here, actually, so that having a bunch of hidden parts of you that are not exposed to public view makes you a much more interesting being. If you want everything that you do to be publicly available, you are a rigid and uninteresting creation, whereas having a bunch of hidden stuff that you don't share and can't communicate makes you much more complex. Oh, that was bad. That was bad. That was a very anti-extrovert thing to say. Okay, yeah.
Are there ways to figure out what patterns, like what those might do? Like you just take out one of the patterns that develops and see what happens to the output?
So absolutely. Like it's not that it's not the case that it's completely like a black box. It's not the case that this is utterly unintelligible. It's just that there's no guarantees that it's intelligible. And a lot of the time, it's really not worth your while to do that. So if you're doing, again, so image recognition, one of the things that the sort of like classic things that they would do with these things, this layer might be edge detection, for example. So you're trying to recognize handwriting. Maybe this one recognizes an edge that goes this way, and this one recognizes an edge that goes this way. And then when you get to this layer, it's more like this one recognizes a loop, or this one recognizes a line, or something like that. So it could be the case that these have sort of recognizable representational content. It's just that that's not what they're for in some sense. And it's not, by no means is it guaranteed that you're going to be able to look inside of it and go, this node is the B recognizing node, or something like that. Typically, people don't try to like dig into these things and figure out what each specific node is doing. Typically, we just sort of let the algorithm work it out for us. The training algorithm, which I promise we will talk about soon. Okay, another thing to notice about these things is that the memory and the processing are in no sense separate. Remember we talked about this with levels of processing, where it seems like your memory and your reasoning are deeply intertwined? Well, that's what this looks like. So there's no part of this. Here's one, just a couple more hidden layers, so 3 hidden layers instead of just 2. And there's no part of it where it's the programming separate from, like, once you've trained it, it remembers how to do a classification. It remembers how to do a classification task. But the remembering is like embodied in the structure of the thing. I don't love the way I said that, but like the processing and memory are deeply, deeply integrated. There's no separate hard drive that's sort of sitting off to the side where it keeps its memory. See what I mean? And that's in contrast to the normal way of organizing a computer where there is separate processing and memory. Right? When you shut down your computer, mostly, I know that they're not utterly, like they're not rigidly and completely separate. There are some parts that are both memory and processing, but mostly the processor and the memory are separate. This one, they're deeply integrated. There's no difference. Okay, so what can these things do? What are they for? Well, they can do complex and messy categorization tasks, like image recognition, voice recognition, things where the inputs are kind of a mess. And I might be the only one in this room old enough to be impressed by that, because it's become a completely common feature of everyday life these days. But when I was a kid, the idea that you could just write down something and a computer would be able to tell what you'd written was mind-blowing. They kept trying to sell it to us, and it kept being terrible. Like they would advertise, oh, it's a tablet that recognizes your handwriting. It didn't. But slowly but surely, we've gotten to the point where now you can do that kind of thing. And invariably, it will be a neural network sort of embedded in that somewhere. So typically, you've got a neural network and a traditional programming system hybridized, put together. So when you plug into, so if you give Adobe Acrobat Pro some like text to scan, right? Mostly the program is standard programming, but there's within it a neural network that does the character recognition, and then it feeds the output back to the traditional program. So facial recognition, medical diagnosis. Also, by way of interest, you can make a Turing-complete neural network. So literally anything you can do with a regular computer, you can, in principle, do with a neural network. And if you want to be really inefficient, you can use a regular computer to instantiate the neural network, which instantiates your Turing machine, just in case you've got a whole bunch of processing power to spare and you're feeling fancy. So this is mostly to indicate that just out of interest that they can do Turing completeness, but just to make it vivid for you that what we're talking about when somebody says they're a connectionist, we're not saying that they necessarily mean that there's no computer anywhere in the process, in the traditional sense of computer. You can run a connectionist network on a normal laptop. And in principle, you could run a laptop like a normal, you could run Windows on a very large connectionist network. So it's not about how it's implemented, it's about the thing that's being implemented. Yeah? So what the connectionists are saying is that your brain is implementing, your brain is neither strictly a connectionist net nor a computer, it's just a bunch of cells trying to survive. But what the connectionists are saying is the important level of analysis for understanding cognition is connectionist networks. Does that distinction make sense? So there's a number of levels on which you could analyze the brain. One is like literally quarks, bosons. You could talk about cells and the cell biology. You could talk about if you're playing chess, like you as a chess playing program, or if you're doing a derivation, you as a logic deriving program. What they're saying is, if you're a connectionist in the robust sense, you're saying the relevant level of analysis for understanding the mind is at the level of a connectionist network. And therefore, the right kind of model to build is a connectionist network. Yeah? Okay. So let's talk about this thing that I've been alluding to, the fourth part of these things. How do you train these things? How do you figure out what the weights should be? And again, we're just going to do the 1986 version of this. So the really simple early versions of this. We'll talk a little bit more about where this goes in the future. But for now, let's start with where we started back in the 80s. So hidden layers do make it harder to train these things. The metaphor I heard for this was that you have to, in some sense, assign blame. So imagine you're a neuron in the head of a human, and that human has just stubbed their toe. And you're in the middle of the brain. You're somewhere, you're not directly connected to the senses, you're not directly connected to motor control. Nonetheless, you need to figure out, was that my fault? So we need somehow to figure out where errors are coming from. Now, in your brain, that's a really difficult problem, and we won't be able to talk about that today. In a connectionist network, the standard way of training these things is what's called backpropagation of error. So, how does that go? Something like this. starting off, just assign weights randomly, just give it something. And then feed it some data, input some data, see how it does. Chances are, because you assign the weights randomly, it will do very poorly. So you say, tell me what letter this is, and it just has no idea. It'll just guess. Okay? Now, having guessed, you can estimate the error. That is to say, you can quantify how wrong was it? How incorrect was I? So it'll give you, if you're doing a character recognition, let's say you're trying to recognize numbers from 0 to 9, it'll give you values for each of them. How likely do you think that was a 0? How likely do you think that was a 1? How likely do you think that was a 2? And you can quantify, given that you know what number it was, you can quantify how wrong it was. Okay, so now you've got an estimation of the error. Using that estimate, you can then look at the weighting and adjust them in the way that generates the largest reduction in error for the smallest change. So there are statistical methods that you can use to say, okay, given that I've got this type of error, what's the smallest change that I can make in the weights to get the biggest improvement? Yeah? These are, without getting into the details of how this is done, I assure you that there are statistical methods by which you can do this. And then you make those adjustments. So the smallest adjustment you can make that makes the error go down the most, and then you feed it some more data. Back through again. Okay? It's still, second time around, it's still really wrong. Like it takes a whole bunch of runs through to train these things, right? You need to feed it a whole bunch of data in order to get estimates of error, take those estimates of error, turn them into adjustments, send through new data over and over and over again. Until eventually, hopefully, if everything's going well, it converges to where the error is very small, or even 0. That's backpropagation of error. That's, or at least it was, the standard way of training a neural network. Backpropagation of error. Okay. So, notice, this is what's called supervised learning. We're in a cognitive science class. We're not just trying to build fancy robots to make ourselves rich. We're trying to understand the mind, presumably. Well, I don't know what you're up to. If you're trying to build fancy robots to understand or to get rich, you might be in the wrong room. Sorry. But, well, I guess this is a prereq. This might be the right room to get into the class where you do that. Okay. But just notice that supervised learning cannot possibly be the way that you learn. Because what does it depend on? Knowing the answer. And when you were a baby, you didn't know the answers yet, right? Right? What supervised learning does is take our capacity to know the answer and use it to train the network. So it's a very efficient method for transferring our intelligence to an unintelligent system. But in no way can it be the answer to how we do it. Yeah?
Basically, pre-computed relevance.
That's right. That's exactly it. That's exactly it. And it's the same issue with the curating the data so that you don't think that all tanks exist in the afternoon and all trucks exist in the evening. Something like that, right? So in the case of curating the data, we need to be able to present it with the right training materials so that it doesn't get confused, so that it tracks the categories that we think are important. Similarly, supervised learning, we need to know the answers. You need to be able to tell it what the correct answer is. And that just cannot be the way our minds operate. Yeah? Well, no? Are there doubts? Yeah, go ahead.
You still teach like a child what they should more or less care about. Don't stick your hand in the fire.
Okay.
If they're smart, they'll do it. If they're stubborn, they'll do it, and then they'll learn probably not to stick their hand in the fire. Hopefully.
That's a weird example because I think that's one of the only, sticking your hand on fire is one of the only ones that you don't have to teach the kid. They'll figure it out if you just let them stick their hand on fire, they'll figure it out pretty fast. So we've got so we're talking about supervised and unsupervised learning. You could imagine some built-in rules. Like if something is hideously painful, that's a really good built-in like, hey, that's an error signal. Shouldn't be doing that. But notice that most of the learning that you've done throughout your life doesn't involve like obvious explicit pain or pleasure, right? When you're learning to do something, typically you're operating, it's not like in a straightforward physical sense, right? So in a straightforward physical sense, success doesn't like, it's not waves of pleasure, and failure is not typically like crashing pain. We mostly operate outside of those things. And we, of course, do supervised learning as well. That's where your money's going. This is what we're doing here. This is, in some sense, supervised learning. But also notice how thin the signal is. I mean, I'm trying to give you as many comments on your papers as I can, given the time I have. But it's not that much. It's a few hundred words at most, right? In some classes, what you get is a number. Like a number. That's your error signal. Sometimes big red X's. That is not a very robust error signal. It's certainly not like the degree of supervision that you get with a neural network, right? So most of your learning, most of your life has been, in some deep sense, unsupervised. You've been generating the signals yourself. And we'll talk about how that's mechanizable to some degree. Like it's not the case that all neural networks operate unsupervised learning. So some do unsupervised learning. We're working, that's kind of that's part of what characterizes deep learning, is not a total absence of supervision, but they need much less supervision. So that's that kind of exciting cutting edge of this stuff right now, learning how to make them much less supervised as learners. Another thing to notice about this backpropagation of error stuff, it's they call a gradient descent style learning. They're moving in a stepwise fashion toward the point of lowest error. And does that remind you of anything from the, yeah? Hill climbing heuristic. This is just the hill climbing heuristic upside down. You're just trying to climb down the hill this time, the hill of error, whereas before it was the hill of success that you're trying to climb up. But it's the same issues, right? So there's the same issues of local optima, so you think you're at the highest point, but actually you're not. Or in this case, you think you're at the point of lowest error, but that was just because that's where you could get by moving in a tiny stepwise fashion. So remember, the backpropagation of error works by the smallest adjustment that you can make to generate the largest change. So you're moving in these little tiny incremental steps. So hill climbing, or gradient descent as they call it, is not a perfect learning mechanism. It'll get you somewhere, but not necessarily the best place. All kinds of strategies exist to try to mitigate this. Sorry, yeah?
What was the difference between this and the supervised learning? Like, how does it decide what's...
Oh, sorry, so this is the thing, yeah. So when you're doing gradient descent, what you're doing is like a hot-cold thing. So you're saying, oh, you did a little better than last time. Oh, you did a little bit worse. So, and notice that there's the same thing with hill climbing. So the hill climbing heuristic is, am I getting closer to my goal or not? That assumes that you've got a steady stream of information about whether you're closer or farther from your goal. So hill climbing, heuristic, gradient descent, they're both forms of learning that assume that there's a ready access to information about whether you're doing it right or whether you're doing better than last time or not. And in pure unsupervised learning, that's usually hard to come by. Okay, so one thing that you can do here is, so far we've been talking about just changing the weights. You can also actually change the structure of the network. So one of the ways that you can get over these, so you're stuck in some local like sinkhole or whatever, you can actually rearrange the connections in the neural network. And as a matter of fact, it turns out that we do that too. So received wisdom when I was a youngin' was that basically your brain starts with all of the neurons that you have, like babies have all of the neurons, and then it's just a matter of paring down. So your life is just a steady decline in the vividness of your experience, and it's just slowly wasting away. Turns out that's not true. So it turns out your brain can generate new neurons and generate new connections. Neuroplasticity, we can do there's adult neurogenesis, which is a nice thought for those of us who are past the point where we're, starting in our steady decline towards inevitable doom. So this is one of the strategies you can use when you're training a neural network. You don't just sort of adjust the weights, you can adjust the internal structure of the thing. How many connections, how many nodes. You can do stuff like knock out a node. So so suppose you're doing this gradient descent, you're doing this your supervised learning, you got yourself to what looks like a local minima. You look like an optimal solution. And then you can just sort of randomly start knocking out nodes. Okay, what do you do without this node and that node? Huh? Smart guy? And sometimes it'll wander around for a while, so it won't stay where it was, but now it can find a new, better solution kind of thing. So you can do stuff like tinker with the structure of the neural network, which, by the way, is like the dark matter of scientific research. Tinkering. They never tell you in the final research report that they tinkered with it. They just messed with it to see what would happen over and over again until they hit on something. They just publish the last thing, typically. All right, so this is plasticity. Okay. So just finish off. We won't go into the third hour very much today. I partly want to apologize for not taking up the whole 3 hours. You're all welcome to hang around and chat about this afterwards. I'm trying to do kind of a compression of this course. The original course that I'm working from involves a lot of digressions and diatribes, and I'm trying to really focus it just to the main stuff that's part of the argument. If I get to teach this again, I'll expand it back out with more examples and stuff like that. But we're in a compression phase at the moment. I hope you don't mind. Okay, so this shift from GoFi to connectionism opens up some new challenges. And I don't want to present these as insoluble. I don't want to present these as, like, I know this course has a kind of rhythm of like, here's an idea, and now I smash it in front of you. That's not what I'm trying to do here. I'm trying to say that these are new questions that open up, new research questions. They're potentially answerable research questions. But for example, you might ask, how is it that the brain is capable of doing language, doing logic, doing logical reasoning? That's a tough question. GoFi had an incredibly good answer for that. How do you do logic? You're made of logic. The stuff of your mind is logical manipulation of symbols. So what do you mean, how do you do language? You're made of language. How do you do logic? You're made of logic. So they had an excellent answer to that question. Really, really excellent. It just tumbled out. And that's one of the reasons why they sort of like, why they assume, it's part of what made it reasonable to assume the GoFi perspective, because that seemed like such an urgent question. Whereas for connectionism, that's a real question that they've got to answer now, right? You got to come up with some way of telling me, how is it that you get language and logic running on a connectionist? Now, yeah.
But didn't you already state that neural networks or connection systems can be Turing complete? If they're Turing complete, would it be a stretch to say that they can emulate or run any language?
That's right. In principle. So then the question is that something that can be done? So yeah, Turing complete in principle. Now the question is, how does that work in practice? Does it, like, how is language actually instantiated in the brain? It's an open research question. Okay. Yeah? Is that reasonable? So, yeah, I mean, okay, some more. Here's a question. which it's really unclear what this is supposed to represent. So how biologically realistic are they supposed to be? I mentioned already the issue of the missing neurotransmitters. There's questions about not all neurons are the same in the brain. There's a variety of types of neurons. What's up with that? Is that important somehow? How many neurons are they supposed to have? So, facial recognition neural networks can have hundreds or thousands of neurons. This cute little fella is a sea slug. It's got a couple hundred neurons, a couple thousand. Where are all the genius sea slugs? An ant has thousands, tens of thousands. Where are all the ants doing calculus? The number of neurons that seem to be necessary for a biological creature to do equivalent tasks like recognizing complex patterns like faces or numbers, these neural networks use relatively few neurons to do it, or nodes to do it. Yeah?
I mean, maybe that's just a byproduct of them having millions and billions of years of evolution
Yeah.
to
Yeah.
do this, as opposed to us who had decades.
Yeah, possibly. Well, wait, shouldn't that argument go the opposite direction?
Well, no, it's if it's optimizing in a lot of really weird ways that happen just kind of over time because of evolution and random chance, as opposed to us poking at the model and seeing what happens. It's just had longer to develop.
So if the idea is that evolution is a better optimizer than we are, neurons are metabolically very expensive. So you want to have as few of them as possible to run your thing. And these guys have this sea slug has way more neural connections than any kind of contemporary neural network. Yeah, sorry. So the argument, the claim was the opposite, that the neural networks that we're operating with seem to have very few nodes, given the complexity of the tasks that they're dealing with, relative to the sea slug, who I kind of wander around and eat lichen. I mean, that's life of a sea slug. Yeah.
Getting back to life of the sea slug, the sea slug is existing in an environment with such rich complexity.
Yeah. So and furthermore, it has to be in some sense a general problem solver, general from the perspective of a sea slug in any case. Whereas these neural networks, as far as I've described these neural networks for you today, they are single purpose specialist systems. You train a neural network for one job and it's bad at every other job. So if you train it up as a face recognizer, it's not good at recognizing tanks and trucks. Do tanks and trucks, it's no good at faces. So all that stuff, remember all that stuff we said at the very beginning about the frame problem and the possibility of a bunch of specialist units? None of that's really solved by the shift that we've done so far. None of those questions are resolved. So you sort of get a version of the frame problem for connectionism just as much as you did for GoFi, because the structures the models that I've been showing you are specialist units. And you might say, yeah, okay, well, what we are is a collection of neural networks. We're a whole bunch of neural networks all interfaced together. And then you get the exact same question about, well, okay, are they talking to each other? If they're talking to each other, how do they coordinate? How do they avoid combinatorial explosion? All of that recurs. Yeah?
Would it be a stretch though to say that that slug, just because of the richness of its environment, I guess it's not super specialized at just eating light. It had to generalize across the scope of many problems.
Yep.
So its ability to be this ultra light and hunter isn't that great. It's enough to keep it going.
Yeah.
Whereas our classifiers, the way they're set up is that they're specialized on something, but when they generalize, they become more garbage and they become forget stuff.
Yeah.
Is that then not a parallel to the slug? Because the slug.
So we're on to a slightly separate question now. So the question of how many neurons they've got, I think you gave a good answer to that already. They just got a lot more problem. A sea slug has a lot more problems than your average connectionist network. But the new question I'd like to ask is how do you deal with the question of specialization? These things look a lot like the algorithms and heuristics we were dealing with before. And then the question is, how do you coordinate the algorithms and heuristics?
I was trying to get at, like, the slug doesn't seem to be like super specialized. It's
No, it's not.
Like, it's a generalized problem solver, but like a portion of its neurons or sections of its neurons do not probably appear to be this super specialized at getting like this super specialized at not being divided. This is super specialized because like, it's just a combination of things.
Yep.
Our models that are not unrealistic.
So not for the sea slug, but for us. The frame problem arises when you're trying to be a human. So, okay. That's enough for today. Next time we will do unsupervised learning.